Alright, so today I'm going to be explaining this important paper with the title Learning Gradient Fields for Molecular Conformation Generation. In conformation generation of molecule, you don't change the topology of the molecule. For example, this carbon, oxygen, hydrogen. You don't change the topology, but you only the angles between them and the distances between them are important. So this paper in 2021, ICML 2021, we study a fundamental problem in computational chemistry known as molecular conformation generation, trying to predict stable 3D structures from 2D molecular graphs. Existing machine learning approaches usually first predict distances between atoms and then generate a 3D structure satisfying the distances, where noise in predicted distances may induce extra errors during 3D coordinate generation. Inspired by the traditional force field methods for molecular dynamics simulation, in this paper we propose a novel approach called conf-GF by directly estimating the gradient fields of log density of atom coordinates. The estimated gradient field allows directly generating stable conformations via Langevin dynamics. In a score matching, first we learn the score. After learning it, then we give it to Langevin dynamics, it generates samples. And so we noticed that estimating the gradient fields of the atom coordinates can be translated to estimating the gradient fields of interatomic distances, and hence develop a novel algorithm based on recent score-based generative models to effectively estimate these gradients. So when we say R, it means these are molecular conformation, R1, R2, and Ri is in R3, it's a 3D vector. So for each node V, it is associated with a nuclear charge Zi, Z sub I, and a 3D vector R sub I, indicating its atomic type and atomic coordinate respectively. So the atomic type is Z sub I, and R sub I is the atomic coordinate. So we can have, for example, when we have a bond between atom I and atom J, then their distance, we have a distance dij between them. So the score function of continuously differentiable probability is gradient of log p. To address the difficulty of estimating score functions in the regions without training data, Song in 2019, Professor Ehrman proposed 2019 that to perturb the data using Gaussian noise of various intensities and jointly estimate the score functions for all noise level. So this is a score functions, and for example, noise level could be sigma I. So we train like this. After the noise conditional score are trained, samples are generated using Langevin dynamics. But equivariance is important. There is a paper called equivariant flow matching that they used a similar idea. They did it for flow matching. Here they are doing it for score matching. So the equivariance can be modeled for any task or any modeling in the generative models that you like. So a function f is equivariant if you transform it, and then first if you do just the transformation function like rotation. This could be a rotation. If you first rotate and then you transform, same as first you transform, then you rotate. So to tackle this issue, because the gradient fields of atomic coordinates should be rototranslation equivariant, the vector fields should rotate together with the molecular system and be invariant under translation. To tackle this issue, we assume that the log density of atomic coordinates given the molecular graph can be parameterized. So the parameterization is interesting. Is Fg composed with g of g? This g of g is a function that maps a set of atomic coordinates to a set of interatomic distances. And F is just GNN. So this graph neural network just estimates the negative energy of a molecule based on interatomic distances. Because here you get D, and then you give D to the GNN. It says that if this has a what is the negative energy of this based on these distances of the nodes that you have in this molecule. So they start from basic principles. So what is the score? The score is just the gradient. Now you have R sub I is just the position. And then by just a chain rule, a simple chain rule, first you can differentiate with respect to D and then D to R. So instead of directly going from F to R, first we have a middle variable, this middle variable D. Now why we do this? Because this comes out because the gradient with respect to D is enough. We can handle this easily. So we have simplified. We have moved from ST R to ST of D. So this is the novelty of this paper. And so we take the interatomic pairwise distances as intermediate variables and propose to first estimate the gradient fields of interatomic distances corresponding to different noise levels. For example, training a noise conditional score network. So the gradients rotate together. It's rototranslation equivariant. So using equation 3, if you use this, it is rototranslation equivariant. It means that the gradients rotate together with the molecule system, so they are and are invariant under translation. The proof is very similar. This core network is rototranslation invariant as it only depends on the interatomic distances. And the vector rotates together with the molecule system. And this is the overview of the conf-GF method. So we first perturb the interatomic distances, d tilde. To perturb it with random Gaussian noise. This random Gaussian noise allows us to perturb it. Because in 3D everything is continuous, so at least the distances and angles and all of these, you can do a lot of things. It has a continuous nature. So sometimes 3D conformation problem is easier than 2D real generation of the adjacency, H type, node type. And then they do the score estimation of atomic coordinates via this chain rule that I said. So once they get score, as I said, they use Langevin dynamics, and this is a score estimation. So for water, H2O, you can see H2 hydrogen and 1 oxygen for different X, Y, and Z. You can see the ST of R. You can see the score of that. So this is a generation procedure using this Langevin dynamics, because you sample, it's a stochastic process until time t. So what is noise conditional score network for distances? So sigma I is positive geometric progression with common ratio gamma. We have discussed this in the previous videos. And we defined the perturbed conditional distance distribution to be this integral. So we aim to learn a conditional score network. So they first embed the node attributes and the edge attributes here using this simple MLP, and then they just aggregated the rest of that is graph neural network, and here for finally for the score. For the score, we use this MLP, and then the loss is very simple in score matching. The loss is very simple because the distances is continuous, so you can approximate the gradient of the true gradient. You can approximate it easily. And so first you initialize the conformation. You say, for example, this is the initial conformation, the angles, the distances, everything. Then you get these distances from G, and then you go from score of D to score of R using that chain rule variable, and then we are now, we just need to learn the score of R, the conformation R. Then we update it because it's Langevin dynamics. It's a recursive, it's a stochastic process. So we update it, and these sigma i's are the noise level, because we have L steps. And there are T time steps in this stochastic process, because for each of these noise level, for example, for sigma 2, we have a different alpha, and alpha is here. So you have a different magnitude for the final noise that you add to that in the sampling process, so they are separate. For different noise levels you have different scores, and when you update it you have different conformations. So then we have the generated conformation at the final time. So there are some measures, for example, coverage and matching score, because we want to see the diversity and accuracy. And for that you need, of course, this root mean squared deviations of heavy atoms between aligned conformations. For example, phi is we call it alignment function. It aligns two conformations by rotation and translation. So these are the results for QM9 dataset and drugs dataset. There are some datasets like QM9, you see it for graph generation, zinc 250K, Moses, here drugs. There are many datasets. Because there are good benchmarks for graph generation. Also, for example, you can use it for 3D conformation generation as well.